All right, so now we're going to talk about critical versus regular events. And the basic idea is if you have, for example, the alpha complexes, and you have this parameter r, and you increase it, what happens, of course, is that you keep adding simplices. It's like well, you add simplices. It's like to the previous complex, and you can ask whether or not, in adding those simplices, whether you maintain the homotopy type of the complex or you change the homotopy type of the complex. Okay, and if you were to just keep the homotopy type the same, then this would be what we call a regular event. And if the homotopy type changes, then this would be what we call a critical event. Okay, so let's say that we have Ri be the smallest sort of radius such that the sort of kith complex, right, is equal to the alpha complex of radius Ri. Okay, so a simplex tau belongs to ki plus 1, but not ki if the following happens, right? If the balls of radius Ri plus 1 have sort of non-empty intersections, non-empty common intersections, with the corresponding intersection of Voronoi cells. But the balls of radius Ri do not. And the way to think about this is that the part corresponding to the Voronoi cells, right? Those of course come from the Delaunay complex, all right? And it's like either they're there or they're not. It's like, and again, it has to do with the intersection of the Voronoi cells. But since it's like these R sub U R spaces, right? If you recall, R sub U R, right, is the intersection, it's like of a balls centered at U about R intersected with the Voronoi cell. It's like centered, well, I mean, it's associated with the point U, right? So if you take the intersection of these things, right, it really sort of the only part which changes is R changes is these balls, right? So all that's really necessary is to see what happens. It's like to these balls. The rest of this stuff, it's like it's already, so the information is already encoded in the Delaunay complex. Okay. So, all right. So if you assume general position, and that the dimension of this simplex you add tau is equal to k, right? The intersection of the Voronoi cells let's just call it v tau. Okay, so this is going to be the intersection over all points u which are contained in tau of the corresponding Voronoi cells, right? So this is sort of a natural notation. Okay, so this is the the intersection, it's like of the Voronoi cells of the points which are in the simplex tau. Okay, is a convex polyhedron of dimension d minus k. Okay. So by definition of r I plus 1, right? These balls centered at the u's, it's like of radius r I plus 1, it's like intersected just a single point, right? By definition. Right. The intersection over u in tau of b u r I plus 1, right, is a single point. Well, I'm sorry, the intersection of this, right, sort of intersects sort of this Voronoi region, right, Vt, at a single point. Let's call it x. Okay. So there are sort of two cases. So two possible cases. Okay, so x could lie on the boundary of v tau. It's just boundary of v tau. Okay. And if that's the case, then there are other Voronoi polyhedra, it's like for which x is also this point of first contact with the union of balls, right? So there are other Voronoi polyhedra for which x is the first contact, if you will, with the union of balls. So let's say that it's like there are two limiting cases, one of which is the polyhedron with the highest dimension and the polyhedron with the lowest dimension. Okay, so let v tau be the one with the highest dimension, and v nu be the one with the lowest dimension. Okay. All right. So the point basically is that this pair of tau and nu is going to be one of those things, it's like which is collapsible, if you will. Okay. So the point is that this means that ki, right, can be obtained from ki plus 1, right, by a sort of KL collapse. So this doesn't change the homotopy type. And as a consequence of that, we call this a regular event. Okay, so nothing interesting happens, if you will, at this regular event because the homotopy type doesn't change. So even though the complex does change, nothing really has happened to it, if you will, right? At least from a topological perspective. Okay, so the case where you have it's like something which is critical, then is that this X is obviously in the interior of this thing. So the second case is that X is in the interior of this intersection of Voronoi cells. So basically, it's not the first contact for any high-dimensional Voronoi polyhedron. So basically what that means is that tau is the only simplex in sort of the difference. So tau is the only simplex in ki plus 1 excluding ki. Okay. Then we call this a critical event, right? So this is a critical event. Because it changes the homotopy type. When R reaches Ri plus 1. Okay? So again, it's like, you know, where we're going to need to be able to track, it's like exactly these critical values. It's like of R, it's like where the homotopy type changes. And that's going to be, again, of interest. It's like when you're trying to see how the homotopy and homology, it's like of these alpha complexes vary, it's like as R changes. All right, so let me just stop here.